No, you were here before. Good to see you all again. Missed you guys yesterday. I was telling Bree at the beginning of class, I usually get up around 5:45 or so. My wife and I go to bed early because the little guy wears us out. So I got up and I looked outside, and I noticed the road outside my house still was not plowed, and there was a pickup truck that was stuck in my road. So I knew there was no way my little red car was going to get through that. So it was still nice to spend some time with my little guy. But what's that? Yeah, I'm glad you enjoyed it. If a class deserves it, it's you guys, because you guys are working hard, and this is not easy stuff. So happy to give it to you. So I think we talked a little bit before about going outside and stuff. I think if we're going to do that, we'll try and do it when it's warmer outside. Basically, it involves you guys pushing my car and then figuring out how much force you use to push it, using some scientific calculations. So
I actually want to do that.
Yeah, so let's wait until springtime, even though we'll be past the force section. It'll probably be more fun that way anyway. We could do that if you want. Sure. Yeah.
Wait, so how do you do it? You just like put it in neutral or something?
Yeah, you put it in neutral, and then I would have you guys push it up to a certain location. Then I'd tell you to stop, and then based on how long it took you to get there, we could figure out the force. So yeah, it's a pretty neat thing. Question: do I look better with my glasses on or off? On? It just looks more me like this.
Yeah.
What do I look like this?
He's thinking about getting contacts, aren't you?
No, I actually have contacts, but my eyes dry up pretty good. So I only wear them like when I'm playing basketball. But so a lot of people actually tell me that I look better without my glasses, and I don't know. I just don't see it.
I don't know. With the glasses, it more suits you as like a science.
Well, thank you. I appreciate that. That was a dad joke too, by the way, because I don't see it. Glasses. That's okay. That's what happens when I give you guys a mental health day. Okay. So here's what we're going to do today. Let's take a look at worksheet number 2. Hopefully you had some time to take a look at the answer key. I think what we'll do today is just go through the 6 problems that we haven't gone through together, and then we'll just call it a day. How's that sound? All right. Let's take a look at the question first here. So, it is long, but here we go. Recall F equals ma. A truck carrying sand is coasting perfectly in neutral at a constant velocity. The sand then begins leaking out the bottom of the truck. What happens to the truck's motion? Does it speed up, slow down, stay the same speed? What do you think? So the mass is decreasing, and it's coasting along. No friction. So what happens? Yes? Could go faster because we're decreasing mass, perhaps? Other guesses on this? Fair enough. So the actual answer is it's going to stay the same speed. The thing is, there's no force that's acting here, actually. F equals ma, but if you have no force acting, then if you're going to decrease your mass, it's ultimately not going to change your speed. So all you got to do is write down constant speed. There will be a little alternative to this question tomorrow, so look forward to that. So let's take a look at worksheet number 2. Number 1, we've got a helicopter. And it's a fat helicopter. It weighs 4,600 kilograms. So for all these questions on the front page, we have to do the exact same procedure. Force diagram, force equation, and then solve. So number 1 is no exception to this. This helicopter has itself a force of gravity. It also has an upward force. That force is going to be larger because it's accelerating up due to the propellers spinning. So you could label this actually whatever you want. If you wanted to label it normal force, that's fine. FP would be fine for force of the propellers. On the answer key, you can see I did FL for lift force, because that's the force that's causing it to lift up due to those propellers. So there's our force diagram. Force equation should be no surprise. Lift force minus gravity equals ma. So, in this case, it wants us to solve for the force exerted by the air on the propellers. In other words, lift force. So if I want to get that so I'm solving for it, I have to take the force of gravity, and I got to chuck it over to the other side. When I do that, the negative becomes positive. And remember, force of gravity is just mg. So ma plus mg. And now we can just plug some numbers into this. So the mass is given to us as 4,600. Acceleration is 2. And what is g? Yeah, 9.8. So then we do a little bit of math, and out pops our answer. Should be about 54,300 or so. Now remember, my answers are rounded to 3 digits. In college, they really pushed scientific notation, so I would see this as, 5.43 times 10 to the 4th. So that's why I do that. If you have more specific of an answer, that is just fine. But yeah, might not be exactly that. That's okay. Questions on number 1? Okay, we did number 2 in class already, so let's do number 3. On to the elevators. So it first says to do a motion map. Again, you don't have to worry about that. But remember, all a motion map is its arrows, and the longer the arrow, the faster it's going. So if you get on an elevator at the bottom, you're going to start at rest, and then it goes up, and it increases its velocity, and eventually you get close to your location, and it's going to start slowing down, and then you'll eventually come to rest, and that'll be the end of that. So you don't have to draw this, but whatever. It is what it is. Maybe you'll encounter motion maps somewhere in college, but probably not. So for this one, we've got a couple different numbers that are given to us here. We've got 840, 1050, and 588. So I believe we talked about what these numbers actually mean in class. So the person sees that his weight is 840 newtons. So that's going to represent his force of gravity. That's what he normally feels all of the time, 840. Then, as the elevator goes up, his weight increases to 1050. So then that 1050 is his normal force. It's how heavy he feels. So for this first part of the question, the dude's in the elevator, gravity is down, normal force is up, and it's larger because he feels heavier. So, before I even look at what I want to solve for, I can just do the force equation. And it should look pretty familiar. And once again, in this case, we're going to be solving for acceleration, it looks like. This is number 3, yep. First half of number 3. We're solving for acceleration, so all I'm going to do is get the little a all by its lonesome, and I can do that by dividing both sides by m. Force of gravity, of course, is mg. So that's the equation that I can use to figure out my acceleration. Questions on where any of this came from? Okay, so normal force is given to us. He feels 1050 newtons. The force of gravity is also given to us. That's 840. And his mass is not given to us. Well, this puts us in an interesting position. Can we find his mass somehow? Yes. Exactly. So remember, force of gravity is equal to mg. We know force of gravity. It's 840. And, of course, g is 9.8. And so, as Gavin pointed out, we can just take 840 divided by 9.8, and then we have our mass. Mass comes out to be 85.7 in this case. So, you do that, out pops your acceleration. And there you go. So it's just a matter of following the same procedure. And when you do run into something where you don't have something that you need, like mass, you just got to try and figure out how to get to it. And that's what a lot of this is. Now, the second part of this is actually not too different. So the second part, we've got the same scenario, but now he's starting to slow down when he reaches his destination up top, which means he's going to feel lighter. So normal force gets smaller. Adorable little normal force there. The equation stays the same, because normal force is still up, gravity is still down. The only thing that's going to change in this whole mess is our normal force is going to be different. And it tells us exactly what that normal force is. 588. So when you go through that procedure again, you'll end up with a different acceleration. It'll be negative this time because it's negative up there in the numerator. And there's our acceleration. And that's number 3. Questions on how this works? Oh, cool. Okay, so we'll do number 4 then next. What color should I use next? Blue or red? Blue sounds good. That is my favorite color. What are your favorite colors? How many people have a favorite color that's green? Nobody? Orange. Yellow. Red. Blue. Good amount of blues. Purple. Black. Brown. White. Did I miss anything? I don't think so. Oh yeah, who likes pink? There we go. Okay. So number 4, back to the elevator. Before we even get started with this, let's just make a little bit of sense out of what it's telling us. We've got 4 people in this elevator, and they are 70 kilograms each. So that's a fair amount of mass right there. 4 people times 70 kilograms is 280. Meanwhile, the elevator itself has a mass. That's 500. So our total mass that we're going to be dealing with here is 780 kilograms. It's kind of helpful just to point that out in the beginning, instead of figuring all this mass out later on. So, force diagram, force equation, and then solve. Now, the elevator itself is what we're looking at here, because it's telling us about the tension in the elevator, and of course we got to take gravity into account. So the force diagram is just going to be of the elevator itself, gravity down, and tension up. I know this is going to be higher and bigger than gravity because it's talking about the acceleration it needs to go up. So if it's accelerating up, this tension force is going to be larger than the force of gravity there. So we're looking for that largest acceleration. And regardless of what it's asking, let's do a force equation. Tension minus gravity equals ma. And this one's asking about acceleration. Force of gravity is mg, divided all by mass in order to get the a all by itself. And that's an equation we can use to solve. So let's put some numbers in. It tells us specifically that the maximum tension force that this cable can withstand is 30,000 newtons. That's why we use tension force in here anyway. That's why we didn't do normal force, because it's specifically giving us information about the tension in the cable. So we've got 30,000, I think. Yep. And then the mass is 780 times gravity, which is 9.8, all divided by 780. And now we can just do a little bit of math, and out pops our answer. .7 meters per second squared. That is a powerful elevator. So you know how G is 9.8. So this is almost 9.8 times 3. So that would be 3 Gs, is what they'd say. You'd feel 3 times your weight. So yeah, that's one powerful elevator. Questions on this or page 1? Good. All right. Page 2 is a whole different animal. So let's turn to page 2. Again, the main purpose of the equations that we're dealing with on page 2 is to start to get you used to using them until we jump into them more fluidly in the next chapter. In the next chapter, you'll learn how to figure out which equation to use for which scenario. Right now, I just want to get you comfortable with kind of plugging the numbers in and the math you got to do to solve for a certain variable. So number 5 we did together, so we'll do number 6. If you're doing a force diagram for 6, you just have a little car with gravity going down, normal force going up, and then because you are laying on the brakes, you'd have a force of friction going in a certain direction, whatever direction is opposite the motion that you feel the car is going. So that would be your force diagram. Those aren't quite as important on this side because we're not doing those force equations for a lot of this. We're mostly using the equations that you were given. And in number 6, the equation that you were given was this guy. So somehow we got to use that in order to figure out what's going on here. So a 1,000-kilogram car, it's traveling 25 meters per second. Brake force is 5,000 newtons. What is the minimum distance required for the car to stop? So which of these letters am I looking for in this question? Yeah, change in X. Total distance traveled there, yep. So let's see if we can plug some numbers in and make this work. So it's going to, if you're braking, you're eventually going to come to rest. So final velocity is 0. Original velocity is 25, so we're off to a good start. Then we've got 2 times our acceleration, which is not given. Lame. So now we've got to find acceleration somehow. So from your acceleration equations, remember it's either change in velocity over change in time, or we could do, F equals ma, so then acceleration is equal to F over m. So we're not going to use change in velocity over change in time here because we don't have any information about time. So we pretty much have to go here. And that's easy enough because we have both of these numbers. The force from the brakes is 5,000 newtons, and the mass is 1,000 kilograms. So then you can just plug those in. I would probably say that the force is negative because it's being applied by a friction force. So your acceleration then would end up being equal to -5. You're slowing down, so the negative would make sense. And you just take that acceleration and you'd plug it in up here. And now we've got an equation where there's only one unknown left. So we'll just do a little bit of arithmetic to get there. 25 squared is 625, if I remember right from the other classes. So I'm going to move the 625 over to the other side, and that makes it negative. 2 times -5 is -10. Change in distance x. So now we just got to divide both sides by -10 here. So that should give you an answer of positive 62.5 for your change in distance x. Because the negatives cancel each other out. Questions on number 6. Alrighty. Number 7. This one's kind of a fun one. This is the sort of thing that you're going to be dealing with a good amount in the next chapter. Things in free fall. And this is a good example of that. So this lady, 65 kilograms, steps off a ledge 10 meters above Lake Winnebago. That's the lake that I kind of grew up on. That's where that came from. So we got to figure out from letter A what her velocity is when she hits the water. And the equation that I asked you to consider for this one was this guy. Now this is the same equation as the last one. The only difference is instead of having change in x, it's change in y here. This is how it's listed on your formula sheet because usually we deal with it with a vertical problem, just like this one is. So because it's vertical, we use y instead of x. So we're looking for the velocity as she hits the water. So that's just right over here. So hopefully we can just plug numbers in and be on our merry way. So original velocity. Now this is a vertical equation, so this velocity would be whatever her original vertical velocity was. And if she's just walking off the ledge, she's not diving down, she's not jumping up and then coming back down, the original velocity then is just going to be 0. Everybody see why that is? Okay. Unless she's giving herself some original vertical velocity, that number is just going to be nothing. So 2, and then we've got this acceleration. What's that acceleration going to be? It is gravity. So a 9.8. But in this example, it's actually going to be negative 9.8. And the reason for that is it's an acceleration. You're speeding up, so that's positive, but you're going down, that's negative. So a positive and a negative make a negative. So then we've got the change in height y. She's going down 10 meters, so that's going to be negative 10. So we just plug that into the calculator then. Except, I suppose I should point this out too. The velocity here is squared. So that means, what do we got to do to get rid of the square? Square root it. So, move this equal sign back a little bit. We got to square root this, and then, of course, we got to square root what's in here. And when you do all that, you're going to end up with 14. Now, here's the thing. There's a lot of little things in this example. Yeah. Why can this be negative? If I plug this into my calculator, it tells me it's a positive number. You're going down, exactly. And remember, the thing with square rooting is when you square root a number, the result can be positive or negative. It's up to you to figure out which it is. So in this case, we know we're going down, so we make it a negative value. Excellent. So that's the first half of number 7. The second half even goes a bit deeper here. No pun intended. But actually, yeah, the pun was intended. Because now she hits the water and she goes underneath it, and eventually she comes to rest 2 meters below the surface of the water. And it was also mentioned that in this example, you got to be aware of this equation again. So now we're looking for the average force that the water is exerting on this girl. So if we're going to look for that average force, we should probably think about at least doing a force diagram and seeing if that somehow is going to help us. So if she's coming to a stop under the water, she's got gravity, and because it's making her come to a stop, her normal force, how heavy she feels, is going to be larger than normal. You know, if this was smaller than gravity, then when she hit the water, she'd still be picking up speed all the way to the lake bottom. But she doesn't do that. It's slowing her down. That's why we know the normal force is bigger here. So if we're looking for how heavy she feels, the average force the water is exerting on her, that's going to be the normal force. Just like on worksheet 1, the force of the floor on the person was the normal force. Yeah?
Why would it be the same if she stopped? I mean, yeah, it makes sense.
Okay, yeah. So, yeah, if it was the same all the way through, she'd keep her velocity all the way down. Yep. So let's do a little force equation here then. This should all look so familiar that it makes you bored. So there's our force equation, and that's what it would turn into if we're looking for normal force here. So, if we have all these numbers, then we're good to go. Let's find out. Her mass is 65. Her acceleration is, we don't have acceleration again. So now we got to go ahead and figure that out. So if we're going to look for acceleration, there are really mainly 2 ways to do it. Yes?
Why wouldn't we use the acceleration we got from the last?
Because for that one, the acceleration is while she's in free fall. Once she hits the water and she starts to slow down, the acceleration is going to be different. So the reason I gave you this equation is because it's really the only way you can find your acceleration in this question. You don't have enough information about force to do the F equals ma thing. You don't have any information about time, so we can't figure out what the acceleration would be for that. So we have to go back to this guy again. So what is the final velocity going to be here? 0, yeah. When she comes to rest, final velocity is nothing. For this scenario, we are considering the period of time from when she hits the water to the time she comes to rest. So how fast is she going when she hits the water? Nope, good guess. We're looking for the original velocity right when she hits the water. Do we know that? We actually do. We found that in the first part. So in the first part, we found the velocity that she had as she hits the water, and that was the negative 14. So that's what's going to go here. And then we've got 2 times the acceleration. Change in height is going to be negative 2 because she goes 2 meters under the water. And that's our setup. So hopefully this can give us an acceleration, and we know that it can because it's only one unknown in there. So, someone do well, actually, we'll save this. We're going to move this to the other side, And then we're going to do some division so that we can get this A all by itself. So this negative 14 is going to come over here, and we'll deal with the negatives once everything's moved. Otherwise, it's going to get confusing. So that's equal to 2A times negative 2. So then what do we got to divide both sides by? Not quite. Wait. To get A by itself, negative 4, because we've got these two 2's over here. And it's like, you know, they multiply each other, so it's like negative 4. There's a lot of little things with this. That's why I'm starting to go over this now with you before the next chapter. So, that's going to be equal to our acceleration. That negative cancels out with that negative, and the square is going to take care of that one. So we end up with a positive acceleration, which would end up being equal to 49. It's a lot of work just to get an acceleration. And that would make sense because she's slowing down in the negative direction. So two negatives make a positive. So there's our positive acceleration. That's going to go in here. And her mass was 65. The G is 9.8. And then we can finish this off. Finally. And there, you have your answer. Oof, that was a doozy. Questions on this? All right. This is like one of those things where you could take a picture of this and then like show it to your parents and they'll be super impressed. So lastly, we've got number 8. This one isn't quite so deep. So this one actually comes almost with a public service announcement. During a collision, a passenger in the front seat of a car slows down from 13.3 meters per second, that's about 25 miles an hour, to rest in 0.1 seconds. So it's a very instantaneous collision. A 25 kilogram child is also sitting in the passenger seat. He is not wearing a seat belt. So letter A says, what is the acceleration of the car? Well, acceleration is equal to change in velocity over change in time. So the original velocity is 13, the final is 0. So change in is final minus original. 13.3, yeah. So you do that math and you'll get 133. And that's letter A. You can already see this is going to be a very dangerous collision. Remember, 29 meters per second squared was 3 Gs. So this is going to be a massive amount of force that this little kid's going to undergo. We'll figure that out exactly later. B, what is the weight of the child? What does the child feel like normally? So that would just be equal to mass times gravity here. So mass times gravity is going to be 25 times 9.8. And that's going to be 245. So yeah, when they say weight, they're talking about how heavy you would normally feel under normal conditions. Letter C, the car driver holds out his arm to keep his 25 kilogram child, who's not wearing a seatbelt, from smashing into the dashboard. What force must he exert on the child? So in this case, when we're thinking about these forces, there's a lot of forces acting on that little kid. You know, you've got gravity down, normal force up, but the only force we're concerned about here is the force that the guy's arm is putting on him. And that's a horizontal force. So in terms of the forces we need to consider, we really only need to consider the horizontal forces. Because that's, we're looking for a horizontal force here. We're not really concerned about the vertical ones. And the only horizontal force is the force from the guy's arm. So we can just simply do this equation, F equals ma, because there's just one horizontal force. There isn't an opposing horizontal force. So mass times acceleration, 25 kilogram kid, times acceleration of 133 from above, and that's going to come out to negative 3,330 newtons. Again, that's rounded to 3 digits, so you might have a different number for the end there. And that's just going to be negative simply because, yep, I made a little mistake here. This acceleration is negative up here because 0 minus 13.3 is a negative number. So that's negative there. That's why you get a negative number for that force. More importantly, though, on to letter D, convert this force from newtons to pounds. Do you think the child will be okay? So kind of a ballpark way to do that is to take your force in newtons and divide by 5. Or you could multiply by a small number, and that's what it's asking you to do here. Multiply this by 0.225. And you'll end up with 749 pounds of force required to keep this little guy from hitting the dashboard. So will he be okay? No. What should he have done? He should have put that seatbelt on. You got it. So make sure not only that you wear your seatbelts, make sure everybody else in your car wears a seatbelt. That'll be good for today.